Okay, welcome back, students. Here we're going to pick up where we left off by talking about friction. So let me zoom in here on this nice slide. So we're going to say friction is the force that opposes motion. So if an object is moving to the right here, friction will point to the left. If an object is moving down, friction will point up. It always points opposite motion. And there's friction present everywhere. You can't get rid of friction. However, many times what we do is we consider the case where there is no friction. So a lot of times we ignore friction, or we say we're on a frictionless surface. And the two types of friction that we are going to include here are static friction and kinetic friction. Friction really depends on the type of surface, right? So here's this like little funny diagram. When you're on snow with skis, that's like not a lot of friction there. You move really fast. But if you're going down a hill with your shoes on, maybe like rubber versus grass, there's going to be a lot more friction there. So static and kinetic friction. The key idea here is that the force of friction acting on an object can be represented by mu times Fn, where mu is the coefficient of friction and Fn is the normal force. But we apply this in two scenarios, the static case and the kinetic case. Static means not moving, and kinetic means moving, right? It's in motion. So static friction is the force that opposes an object before it's moved. So imagine there's a giant boulder here, and here I am, boop-a-doop-a-doo, I apply a force. So I'm applying a force to this boulder, and I hate drawing it like that. Why don't I say, I'm going to get rid of myself, and then we'll just know I'm applying a force. I'm applying a force of, say, 10 newtons to this, and it is not budging, right? It's not moving at all. Well, if it's not moving, then you know the object is in equilibrium and the net force has to be 0. So that would imply that there's a friction force, a static friction force, because the object is not moving, equal to what I'm applying. So there's got to be a 10 Newton friction force. Let's say I increase my force to say 20 newtons and it's still not budging. Well, now the friction force is 20 newtons. I'm super strong, so I increase it to 100 newtons and it's still not moving. Well, the friction force here has got to be 100 newtons. If it's not moving, it is in equilibrium. Now, let's say I increase it to 120 newtons and it just begins to move. Well, now we've overcome the static case and we've moved into the kinetic case where the object is in motion. Now, in each instance, we can quantify maybe the amount of friction that is present between two surfaces given the coefficient of friction, mu. And we have two coefficients, whether it's static or it's kinetic, because the amount of friction is different whether something is stationary versus if something is in motion. So static friction, this increases in magnitude depending upon the force applied to move an object. We saw that, right? If I push with 10 newtons, friction pushes back with 10 newtons. 20, it pushes back with 20. It's always going to match me. A maximum is reached. When a maximum is reached, then the object moves into kinetic friction, right? So, right, static friction, it increases, and then we hit some breaking point and kinetic friction happens. And if you notice, the kinetic friction is lower than the static friction. Static friction is always higher than kinetic friction. It's harder to get an object moving than it is to keep it moving. Once the object's in motion, you don't have to work as hard to keep the object moving because kinetic friction will be less. So the coefficient of friction, here we have it, this mu, and these values are found right on the reference table. It is a unitless number that depends on the type of surfaces that are in contact, and it relates the amount of friction that is present. So if you look like rubber on concrete, there's a kinetic coefficient of 0.68 and a static coefficient of 0.9. If the concrete is wet, look what happens to the coefficient of friction. It's smaller because there's less friction here. It's 0.58. Rubber on ice, there's not a lot of friction present. The kinetic coefficient is 0.15. A waxed ski on snow, well, there's like no friction present, right? When you're in motion, the coefficient of friction here is 0.05, and if you're stationary, it's 0.14. All right, so remember, right? This is not in motion. This is if you are in motion. Note here that the coefficient of friction is a unitless quantity, and it is always less than 1. So let's do an example here. It says a 24 kilogram crate at rest on a horizontal floor requires a 75 Newton horizontal force to set it into motion. Find the coefficient of friction between the crate and the floor. So here we have it, right? I have to apply a force. So I'm going to put my applied force as 75 newtons. And there's a force of gravity, I should say that. I can determine the force of gravity. Fg is just m times g. So that's 24 kilograms times negative 9.81 meters per second squared. So 24 times 9.81 gives me a force of gravity of 235.4 newtons. We're on a flat surface, so that also means there's a normal force, which points up, of 235.4 newtons. And I have to apply 75 newtons of force to set this into motion. So if I'm applying 75 newtons of force and it's not yet moving, right? I'm setting it into motion. Well, then that means there's got to be something that points opposite and that applied force. And that's the friction force. And it's going to have the same magnitude, right? If I'm applying 75 newtons of force, it is not yet moving. I'm setting it into motion. So the force of friction also has to be 75 newtons. And then it transitions into the kinetic case, right? We're moving. So we want to determine the coefficient of friction between the crate and the floor. So the force of friction is equal to mu times the normal force. Now, if we look, we're in the static case because we're not yet moving. So I'm going to put a little s here. Now, the force of friction we said is 75 newtons. And I have the coefficient of static friction times the normal force, which we solved for, as 235.4 newtons. I'll divide both sides by 235.4. And we get our coefficient of static friction. So 75 divided by 235.4 gives me a coefficient of 0.32, unitless and less than 1. Now, once the object is in motion, maybe my applied force is less. I don't have to apply as much. And the coefficient of kinetic friction maybe is smaller. Maybe it's like 0.21, okay? Just picking values here. Let's look at another example. It says determine how much force would be required to begin moving a 250 kilogram slab of rubber on dry asphalt. Okay, so here we have it, right? I want an applied force, Fa. I don't know what it is, but I want to set this thing into motion. If I'm setting it into motion, it's not yet moving. This is the static case. I know there's a force of gravity which points down. There's a normal force which points up, and of course there is friction which points opposite my motion. So let's determine the force of gravity. Fg is equal to mg, so I have 250 kilograms times negative 9.81 meters per second squared. So 250 times negative 9.81 gives me a force of gravity here of 2,452.5 newtons. We see that when we're on a flat surface, the normal force is also going to be 2,452.5 newtons. Okay, so we've got that filled in. We don't know the applied force. I don't seem to know the friction force, so those are all empty. But we do know something else here. We know we have rubber on dry asphalt. And we also know that we're trying to set this into motion. So we're not yet moving, we're static. If I just scroll back up here, rubber on asphalt, dry, the static coefficient of friction is 0.85. And that's taken right off your reference table. So I'm going to say mu s is 0.85. So our relationship here, the force of friction that's acting on an object, is equal to the coefficient of friction times the normal force. So I have the normal force, I have the coefficient. I'm going to plug in 0.85 times the normal force of 2,452.5 newtons. Tells me the force of friction is approximately 2,084.6 newtons. So that's over here, 2,084.6 newtons. If this object is not yet in motion, if we're setting it into motion, then that means my applied force has to be equal to the force of friction. So not only are we doing some math here, but we also have to make some assumptions with the concepts of physics